Okay, can I start?
Yep.
Welcome everyone to the next seminar on probability stochastic process from IME USP. And this week we have with us Guilherme Silva from São Paulo's University also. So welcome Guilherme, and thank you very much for accepting the invitation.
Yeah, thank you. And thanks all of you for coming. It's really nice to give a talk here. I have been to IME USP only for personal reasons, never really for academic reasons. So it's nice that I am now coming to give a talk, although I'm not exactly coming, right? But okay, it's better this way than no way, right? So yeah, so thank you all for coming. Yeah, I'm going to be talking about TASAP, total symmetric simple exclusion process, and some connections with integrable systems. Most of the things I'm going to talk about are actually, I'll try to put an overview at the beginning, but the results, the new results I'm going to talk about are joint work with Jinho Bacon and Jipeng Liu. And perhaps towards the end, I just give some directions. It's also joint work with Andrei Prokhorov. It's actually work in progress. Okay. It's nice to give a talk in a probability seminar because you don't have to explain what the central limit theorem is. So you're all very familiar with that. I just want to highlight some points here. Yeah, so the classical central limit theorem says that, okay, under some conditions, you take sum of random variables, independent random variables, you scale them appropriately. What you get is the fluctuations of the sum. They converge to a Gaussian distribution, right? Just a few things I want to stress because I'm going to make some comparison later. So the first thing is that the original statement, or perhaps one of the first statements, or the first statement, appeared in the works of Moivre and Laplace, and that it's already dating from the beginning of the 19th century, right, for Bernoulli random variables. Why Bernoulli? Because everything is explicit; you can just compute it, right? And it took about 100 years to get to a formulation closer to what we know as central limit theorem, which is for general random variables, right? And this was by Lindbergh and Levy. So around 100 years to get to that point. So that's the first message I want to say, to stress here, is that 100 years to go from explicit calculations to something that was really based on principles, not explicit calculations to some extent, right? And also meaning that also 100 years to go from a particular case to a very general statement. And the second thing I want to highlight is that there is independence. We're talking about independent random variables, so no correlations here. Right? And I'm going to talk about mostly TASAP, but our motivation comes from let's say central limit theorems, but for correlated systems. Let me just give you some very short glimpse of what I mean, of some of those models that are related to what I'm going to talk about. So if you look here on the top left corner, I hope you're seeing my pointer here. What you see here is an experiment done in the 2010, 2012 by a group of Japanese researchers. And what they do is that they have a crystal liquid and they shoot a laser right in the center. And this crystal liquid gets excited and changes the state. This laser shot right at the center, but then all the states, the nearby states, like just interact with one another, and you see this growing interface of excited crystals. And I want you to pay attention to this interface that's growing. So difference between gray or light gray and dark gray. So this interface is random, and of course, we'll want to describe, okay, it's random, but what can we say about this growing interface? In particular, what can we say about fluctuations between the dark region to the light region? Can we describe the fluctuation between those two regions in this growing process? Another phenomena coming also from nature, you can see, well, we cannot see much, but in some countries people see quite well, which is like glazing windshells. And so basically ice is dropping on the windshield of a car, and it creates a certain random surface, if you may say, that you see over here, right? And you have this transition between what is really ice and what is just glass, So there's this interface, which is also random, and you can imagine that is growing over time because there's more and more drops of ice coming down. The third model, this is more like a mathematical model that you see in the center, are non-intersecting random walks or non-intersecting Brownian motions, or I should say non-intersecting Brownian bridges, because they all start at the origin and end also, let's say, at 0, right? And time is running here horizontally. Of course, so you have the dynamics running over time, but there's also this random interface that's created here at the top. And once again, what you want to understand is what happens with the fluctuations around this top region here. So what can you say about the transition between regions where you see walkers and the regions that you don't see walkers? Can you describe fluctuations over there? And another model that you see here on the 2 pictures actually on the bottom is the so-called stochastic 6-vertex model. There's a whole, there's several ways to describe it, but you can imagine that, like, if you, let me focus here on the left picture first. Imagine that you have certain paths, infinitely many paths coming on the left side here, right? They all come and they walk on the integer lattice, and they are subject not to intersect, so they cannot intersect. Whenever they're walking, they decide, let's say, whether they want to jump, whether they want to keep going straight, or let's say move upwards, right? So you see that here, the path at the top bottom, when the path at the top, the lower bottom, when the path at the lower bottom decides to move, it's creating a pushing effect so that all the other paths also want to move upwards. Right? And then you see this sort of movement. So those are like lots of paths this way, constructed this way. And you can see that it creates certain interface here where you have fewer paths here, more paths here. And actually, and all the paths that are here, they are deterministic. Although, but the interface that you see here in the middle is not deterministic, right? What you see over here on the right is just like a picture from the top, but when you associate with a height function to describe the density of paths here in the middle region, right? Or the density of, let's say, it's not exactly the path, but really because you sort of you symmetrize it some sort of, so that you see that right in the middle I have a growing interface, sort of a mountain shape that go up, middle, and down. Right? Anyway, there it's a model, should be more mathematically precise about that, but okay, just to highlight that there's also a sort of a growing interface over here. And once again, we want to understand transitions between regions where you don't see any path at all, or regions that you know exactly what's going on, towards regions that you have some randomness, some sort of stochasticity here. And actually, to some extent, the nice thing about the stochastic 6-vertex model is that it encodes several other models. That's why it's also interesting. So sort of can look at projections and we cover other models, including also the taste set I'm going to talk about today. Anyway, but the question is, what do they all have in common? As I hope you realize, I was stressing always this fluctuation between, let's say, random regions and deterministic regions. And that's exactly what they all have in common. If you start looking at transitions between those deterministic regions and those, or better to say, from the, let's say, stochastic regions to the deterministic regions, you look at fluctuations around the growing interface, they all have the same statistics, right? But what exactly are those statistics? So this is regarding what is nowadays called as KPZ universality conjecture. And what does it say? It says the following. Imagine that you have a growth process, 1 plus 1 dimension growth process. So you can really think about it, for instance, as this growing interface here of ice. So it's growing, let's say, in this case, vertically, right? And imagine that you have this, okay, so this stochastic process, stochastic growth process. And imagine, okay, you wait for a very long time and then start computing stuff, and then you see that the fluctuations around of this interface, of this growing interface, around like its expected, around this expected position, you realize that the fluctuations there scale of order of time 1/3. When time is very large. And the spatial correlations between points horizontally, they scale around order 2/3. In what sense? The sense that if you scale the fluctuations order 1/3 and the spatial correlations order 2/3 with time, then what you get is some non-trivial limit, some non-trivial object. And if you do have a non-trivial object under this scale, in the KPZ universality conjecture says that this object that you get, non-trivial object, should be universal, should be the same. It doesn't matter which model you're talking about. Right? Yeah, so this is to say that if you wait for a very long time, the dynamics of your process, the evolution of your process becomes universal. It's just the same, doesn't matter the model you start with under some conditions, right? Or in other words, if you start computing statistics for different models and you scale things appropriately, what you're gonna see at the end is that the fluctuations of those statistics, they should converge to the same limiting distribution. No longer Gaussian because they have correlations, right? And this limiting distribution or this limiting evolution or this limiting process is universal. It may depend on where you started from, but the dynamics, once you start growing, the dynamics that you have, these dynamics is universal. It doesn't depend on the model you started with, perhaps only on the initial position, whether you start, let's say, with a flat region, as with ice in the windshield, or if you start with a circular region, as it was, for instance, the crystal liquid, right? But the evolution afterwards is governed by the same law. And what's this law? This law is what's called a KPZ fixed point. But actually, it has been around forever to construct this limiting law. It was only constructed recently by two groups of people, Matetsky, Kostel-Ermenik in 2016, and actually the Wegner, Ortmann, and Virac a little bit later, they constructed even like in more detail what's now called as KPZ fixed point, which is this limiting object, this limiting fluctuation field that should govern all the models in the KPZ universality class. But although, and the story is, you start back in 1980s when you have KPZ equation, and then in the 1990s you have random matrix theory. People start seeing statistics, similar statistics in different models appearing here and there. In the early 2000s, people realized, well, perhaps there's some limiting object in the background because we all compute those we all compute those limiting statistics, and they happen to be all the same. What's going on? And then they start to conjecture, well, there should be a limiting object behind it. But it took forever for them to actually construct a limiting object, which is now called the KPZ fixed point. But constructing the limiting object is not the end of the story. You still have to prove that under general conditions, several different models converge to the same limiting object. And at this stage, we still are at the level of model-dependent proofs. What do I mean by that? Remember that in the CLT, first people proved CLT for Bernoulli. 100 years later, they proved for under general conditions. Let's say that we are right in the middle of the story. Now we have some proofs for some models, we have some general proofs that those models converge to KPZ fixed point, but still far from actually a general proof, as in the KPZ universality conjecture that just relies on non-trivial scalings of the height and spatial correlations. Right? So in that sense, we're still like relying on models, relying on formulas to verify KPZ universality. Well, there's a drawback, but on the other hand, also we have concrete formulas to understand this limiting object, and even its construction is not exactly easy. And so like having like some nice ways to analyze it through, let's say, as the limit of certain objects is also something that can be of interest. And today I want to be talking about one of the canonical models to study in this KPZ fixed point, which is the total asymmetric simple exclusion process. So this is one of the models for which we know that under general conditions, or for some initial profiles, for some initial conditions, we have convergence to the KPZ fixed point. This is a recent result. And in a certain sense, is one of the ways to studying this KPZ fixed point is through studying statistics of the Tay set. And that's what we're going to do today. So I plan to introduce it, although probably many of you have already seen, but I will reintroduce it again, talk about some limiting statistics that appear over there, and shift towards its periodic version. So in a certain sense, what should be the periodic KPZ fixed point, which has not yet been described, but anyway, the periodic set is expected to describe in the limit to converge to certain periodic version of the KPZ fixed point. So in a certain sense, the perspective is that we are describing some universal limiting statistics. Right? Okay, everything was just mumbo jumbo, lots of philosophy, nothing really concrete. But let's start talking about concrete stuff. So this is the data total asymmetric simple exclusion process. Perhaps some of you already, or many of you have already seen it, but let me just go over it very quickly. And the model is that probably many of you are familiar with, is that you have certain particles on the integers, and particles will start jumping according to certain dynamics. For us today, we're going to place particles in all the negative integers. And on top of that, I'm going to place also a function here, which is in this case just the absolute value. So it's just like a corner, downwards corner. Okay. Okay, how exactly the dynamics of the ASAP? So particles have independent clocks, and then the clocks start ringing at random times, right? And then, okay, let's say you start running your model, and then you wait until the first clock rings, and let's say that the first clock that rings is the clock for the first particle. Okay, for the first particle, so then the clock rang. So what you do? The first particle then just looks forward and jumps, right? Because the clock told the particle to do so. Okay, once the particle jumps, we just create also some dynamics on the graph of the absolute value. What you do? You just shift a downwards corner to an upwards corner. So this downward corner will now become the upwards corner. Okay? So that whatever is happening down here on the particles, you will see somehow in this interface, right, in this graph. You keep moving forward. Let's say that the second clock to ring is the clock of the third particle. The particle looks forward, hey, I'm blocked. Oh, but then I have the exclusion rule. I don't jump, right, because I'm just blocked. And so the third particle just stays still. And then you keep running. Right? Perhaps the next clock rings of the second particle, the particle jumps, and the corresponding corner moves from downwards to upwards. And you keep running the dynamics, you can imagine that this graph is going to start to grow. And although you started from deterministic position, both for the particles and for the graph, everything runs stochastically, right? And you can imagine this graph is going to start to grow. But I don't want to rely only on your imagination, so I want to show you also some animation. So what you see here is not just like 4 particles, but you see 180 particles. They're all sitting very close to one another. And here you see 2 graphs, different colors, but the same graph at this moment. What are those graphs? So in blue here, it's going to be the random graph. And in green, there's going to be a green graph, which is going to be its expected value. Right now, they're right at the same time, at the same position, right? Now I start running the dynamics. There you go. They're running, I hope you can see. And you see that the blue graph is really the stochastic one, so it's growing, but shaking a bit. And the green one is, you can see it as its expected value, right? Let me just run it one more time. You see the particles moving down there, and then you just keep track of the particles by looking at its random graph or its random height function, right? And what we want to study are the fluctuations of the height function, the blue one, around its deterministic position, which is the green one. When time runs for very long, right? So this is the same picture, but now let me then just quickly explain to you the scaling. So according to the KPZ scaling, what you should do? Well, we look at a time window very far away. So time here is proportional to a constant L, and this L is very large. So imagine that you waited for a very, very long time. Right? And then you look at the window of the following way. So the position here of the window is more or less L. And then you look at the horizontal window here, which is order of L 2/3. Why? Spatial correlations according to KPZ scaling should be of order 2/3, which means that if you fix, let's say, at a particle at the origin, and you look at a particle that's much, much larger than at a position much, much further away than L 2/3, then those two particles should be decorrelated or should have very small correlations, right? So the correlation happens really at the window, horizontal window of size 2/3. And likewise, correlations here for the fluctuations of the blue one around the green one are expected to be of order 1/3 with time, scale of order 1/3 with time. Okay? Then look at this, let's say, rescaled height function. I'm here denoting by tau. Tau is my new time, rescale time, and gamma is the rescale horizontal position. Back in 1999, in the context of last passage percolation and then translated to TASAP, Kurt Johansson proved that basically you get some limit under this scaling for the height function. There are constants here and there, but really what's important is that you have those scalings, and here you have then certain variables. Tau is the new time, the rescale time. Gamma is the horizontal position. And X here is your rescaled height variable or fluctuation variable, right, or distribution variable. So Kurt Johansson proved that you have limiting fluctuations. So the fluctuations converge to a function here that I'm calling FKPZ. This function is really a distribution in the variable X, but this distribution depends on two parameters, position, horizontal position, and depend also on rescale time, tau, right? So this was a result of Johansson done in the context of TASAP, exactly the model that I just described. Right. Okay, donkey. But what exactly is this function? So this function was realized that this function was exactly the same function that appeared in random matrix theory, that more or less about a few years before the work of Kurt Johansson. And this is what we call the Tracy-Widom distribution, F2. So actually, as I said, so this FKPZ, I'm calling FKPZ, is a function of three variables. One of them, X, is the distributional variable, but in fact, it's just a what we call self-similar function, in the sense that it's just a rescaled version of a function F2 of only one variable. And already at that point, Kurt Johansson already wrote everything down in terms just of F2, not FKPZ, but I'm keeping FKPZ for a reason I'm going to tell you in just a moment. Right? Anyway, so yeah, so basically all the fluctuations are encoded in this single variable distribution, which is the Tracy-Widom distribution, which appeared in random matrix theory. And here it is. So you see here that you have, what I'm doing here is just plotting it. So in blue, you see a Gaussian, and in red, you see the Tracy-Widom. And here, I'm really putting the Gaussian with the same mean and variance as the Tracy-Widom. They're almost the same, but not quite. If you look at the large tail here, they are different. So Gaussian is square, e to minus x squared, constants over there, right? The Tracy-Widom is really e to the minus x the power 3/2, if I'm not mistaken. No, e to minus x to the power 3, actually. And here's also a completely different tail. Anyway, they are different, genuinely different functions, right? Okay, but what exactly is F2? Okay, it's a graph. Well, the graph is a graph, right? But what exactly is mathematically? So, as I said, it appeared first in the context of random matrix theory, and appeared first in the work of Peter Forrester, where it appeared as what we call a Fredholm determinant. But bear with me, ugly formula, but it's not that, well, I'm going to make it simple in just a moment. There's a way to define it in intrinsic terms of functional analysis, but here we can just take it as a series. Right, so what you do? Well, this F2 is a series where each coefficient here is a multiple integral, and the number of integrations in each coefficient depends on the index of the coefficient. Okay, well, what sort of determinant? Well, the determinant, what sort of a series? The coefficients here, those integrals, they involve a certain determinant of size k as well. So k, you take a k determinant, k integrals, and put in a series, and then you sum. And in this determinant here, it's built out of all of a function of one single variable, which is the kernel for the operator. Anyway, important here first that this kernel is basically depends on a special function, the array function, and in particular, it depends on the parameter x, right? Again, ugly formula. What's important here? Okay, it's a series with certain integrals and determinants. But everything, all the variables here, which is x, right? All the distribution variable is really encoded just in this function of two variables, which appears in a simple form, what we call a Hankel product of Hankel operators. Anyway, so you take your variable x, you place in a function of two variables, and then you compute the determinant of several variables. Then you integrate in those all those variables, and then you sum, but then you get there. Okay, not very appealing, but it is what it is, right? Okay, but shortly, actually about the same time, but the work appeared later. Tracy Weedon realized that there is a somehow more appealing formulation of this Tracy Weedon distribution, and this formulation is in terms of integrable systems or a particular ordinary differential equation. This is simpler to state it. What Tracy Weedon proved is that you take this F2, this distribution, and then you take its log, take two derivatives. Okay, you get a new function calling it u. This new function solves a second order ODE nonlinear. This ODE is called the Painlevé-2 equation for reasons that will take. It's a nice story, but okay, I'll go into that today. But one thing is funny. Painlevé was actually a minister of war in France during the First World War, I guess a period of the Second World War, but also a mathematician for fun. The equations are named after him because he did all sort of he did like a classification theory for second order nonlinear ODEs. That's why the name comes from. Anyway, they're very nice equations, lots of nice properties here. Okay, there's a certain particular solution to this equation given by specified by certain asymptotics on infinity. You pick up the solution, you integrate two times, you take exponential, and then you recover your F2. That's the moral of the story. So yeah, okay. So you have this new distribution, and here is really so this result of Curtin-Hanson was to some extent what's really striking. Why? Because I said this distribution appeared in random matrix theory first. Those two works concern random matrix theory, and Curtin-Hanson was, if not the first, one of the first, perhaps other works about the same time, also showing that several different models. So I was talking about TASAB, a discrete model. He proved that fluctuation of this TASAB have exactly these same limiting statistics, which appears in random matrix theory. Right? So that sort of put a thought on people. Okay, how much of universal is that? Are there other models for which we still have the same limiting statistics? And this is sort of the starting of the story of this KPZ universality. And then people later realized that it was also connected to KPZ equation that appeared like 20 or 15, 10 years before those works in random matrix theory. Anyway, story short, what you should take from this: start with TASAB, you associate a growth process with the TASAB, which is the random growth, this random growing function. Look at fluctuations, and these fluctuations are given by this distribution, Tracy Weedon, which is universal, right? It appears also in other models. Okay, nice. Okay, that's for the TASAB. Let's say it's more or less classical results. But now let's put something else into the game. What is that? It's periodicity. So the picture that you see over here is basically the same picture for the TASAB that you saw before, but now with periodicity. What do I mean by that? So let's look at this interval here. So you have here the red dots, which are the particles. They're all together. Here you have just blank space. And the particles and the blank space will form our fundamental period. Right? So the dynamics here of TASAB is exactly the same. You start, each particle here in this fundamental period has its clock. The clocks are independent, start ringing at random times. Particles start jumping, and now you input periodicity. What does that mean? It means that whatever this particle here does, the corresponding particle here in this other group will do exactly the same. The corresponding particle here in this other group will do exactly the same, right? So you have a periodicity effect. And of course, you have also a high function on top of it. But now, okay, you want to glue things so that you get a continuous graph. So that's why you see sort of slow growth in the picture, right? So just like you place your absolute value graph here in the fundamental period, but then you glue its pieces so that you get a continuous function. But see the difference. So at the very short time, the particles start jumping, and they just feel the particles on the same group. But at some point, the very first particle here will hit the particle on the bottom on the next group. In other words, the first particle here will become correlated with the particle at the very bottom, at the very last particle. So this creates a different dynamics at a certain stage, right? Because before, the first particle will never see particles behind it, but now eventually it will start feeling particles behind it. There's this correlation, and now particles become correlated. Okay, let's see how this works. Here's for short time, dynamics just run as it was. And you see at some point, the first particle will hit the block, meaning that starts to become correlated with the one on the bottom. And then you create certain dynamics, right? So of course, it is to be expected that for a very short time, dynamics are just the same as the classical phase set. But at some point, all particles become correlated, so dynamics and corresponding fluctuations should change. And there's even here that if you sort of start following, you see that there's even here a distinction where there's this corner, but at some point, when the last particle hits the first one, this corner starts to smooth out somehow. There's sort of a shock dynamics created over there. So anyway, very interesting things going on here, right? Okay, so this is the periodic ASAP. The question is the same. What we're going to do, we want to run for a very long time and understand fluctuations, right? But you see that now there is a clear distinction. Depending on the position, horizontal position that I'm looking at, I may have different phenomena. For instance, if I look at right at the position where particles could shock, could collide, and I look at the fluctuations here, there's no reason to expect why it should be the same as in the center, especially because here I had a corner, here I didn't, right? So, and even right afterwards, the correlations are different. So really I expect now some non-trivial difference if I move the position where I'm looking at fluctuations, the horizontal position where I'm looking at fluctuations. Okay, same story. Run for a long time, we scale things appropriately, and what do we expect? Well, there are two regimes that were described in the physics in the 90s. The first is what they call the superrelaxation time scale, which is when the time runs for a very long time, much longer than the period. So what you do now is that we scale time, we scale everything according to KPZ, but you also have to scale the period. So you're putting more and more particles and scaling also your fundamental period to grow also with time. But if your time is growing much faster than actually your fundamental period, well, eventually all the particles will collide and will become strongly correlated. So the one particle will only move if all the particles move together. So it's almost like a random walk, because all the particles are just like so strongly correlated that they move together. And this is what's super relaxation time scale. On the other hand, if your period is rescaling much faster than your time, it means that the particles never get to collide with different groups. So the dynamic should be just the same as the standard ASAP. And this is what they call super-relaxation time scale. Well, there should be something between them, right? And this is something between what they call relaxation time scale. Right? Okay, there should be some intermediate regime, interpolating regime between standard ASAP and just random walk. And this is the relaxation time scale. And if you think a bit about the KPZ scaling, you know that the particles get correlated, the spatial correlations in the classical ASAP, they happen of order time to 2/3. So if you scale your period exactly that way, so you scale your period exactly time to 2/3, you will be exactly this critical scaling of KPZ scaling, but not quite, because the particles will be exactly critically correlated. And this is the relaxation time scale, when you time scales as the period. Okay, this was already predicted in the physics for perhaps like the late 90s, but it took a while for mathematicians to figure out what was going on. Yeah, okay, word of warning. Although you can, for the same position of particles that you put here on bottom, you could put different graphs to start with. I'm always going to be starting with this graph that you see here, sort of star-like graph. You could do for different graphs, but the form must change. So I'm only going to be talking about this step-like, which is called also periodic step initial condition. Right? Anyway, as I said, so everything for this step in the initial condition was described in the physics, like, or was predicted in physics, although they couldn't really get formulas or anything. But was our simulation they already had and whatnot. And it took a while for people to start writing mathematical statements. And actually, the first statements, the first time that some limiting fluctuations were computed in this relaxation time scale works more or less recently. So in works of Bacon-Liu, 2018, and also Silva and Prolak, 2016, the two works came more or less about the same time. But Silva and Prolak is more like in the physics side. He was, let's say, rigorous enough for physicists, but not so rigorous for mathematicians. The papers came more or less about the same time, but the official date of publication, they are different because of that. Anyway, what they did, certain scaling, you scale height function, whatnot, you compute fluctuations in the appropriate regime, in relaxation time scale. And what they computed is that, okay, you have a limiting distribution. This limiting distribution, okay, don't care about the scaling, it's just convenience, but depends again on parameters x, which is the fluctuation variable or the height fluctuation, gamma, which is the horizontal position, and tau, which is the rescale time, right? As it was in the TASAP. But remember that there in the TASAP, I showed a formula like that, FKPZ, in 3 variables, and right afterwards, I showed that it was actually written in terms of one single variable. This is no longer the case. This is really depends non-trivially on the 3 parameters. Okay, and how exactly is that? Okay, it's not so simple formula. What do you do? Okay, several things here. So this function, to compute this function, you have to consider a counter integral on the plane, a small circle around the origin. And what you do, you have a certain weight here, a new Fredholm determinant, depending on all the parameters, and then you integrate. So sort of, you take Fredholm determinant, depending on several parameters, you weigh them, and then you make a superposition of them. Lucky enough, although everything is complex, you get a probability distribution. Okay, it's an ugly formula, but it is what it is. A1 and A2 and B, they're explicit and they don't depend on parameters. So the dependence of the weight on x and tau here is nice. The Fredholm determinant is quite ugly. Didn't write the formula. How they got there? Well, they wrote down forward Kolmogorov equations for the transition probability, solve those equations in coordinate Bethenstadt, okay, and then they take limits, and you get a formula, right? Okay, they spit out the formula, this is the formula, just leave it that, and what do you do with that? Well, that's our work. So we were trying to understand, okay, you had this ugly formula, what can we say about it? Okay. Okay, so let me then show you some of our results. And along the way, I'll always be comparing with the classical TASAP. Well, it's nice to compare. Right? Okay, so I showed to you several formulations of the classical TASAP. So for that FKPZ function, which is Tracy-Weedon draft, one of the formulations was in terms of Fredholm determinant. And in practice, what it means is that this FKPZ can be written down in terms of determinant, and this determinant is built out of all of a single function. Okay, through that procedure, you take some function, place a function of 2 variables, compute integrals, compute series, and whatnot. Anyway, but everything was encoded in this function, which now I write explicitly. Over there was just as area, I made a shift and wrote down everything explicitly. This single variable function is now an integral on the complex plane on a contour. I take this contour as in blue here. And the heart of everything is happening here, which is just like an exponential where time appears with the cubic term, horizontal position appears with quadratic term, and height fluctuations, x, appears with the linear term. Right? Anyway, okay, it's formula. And the first result that we have a somehow similar looking formula. How does that look like? Well, you still have to live with this superposition-like formula, but what we managed to do is that we managed to compare at least the Fredholm determinants. Before we had a single Fredholm determinant, now we have a still superposition Fredholm determinants. But this new Fredholm determinant, which is different from the original one obtained by Bacon-Liu and also Prolak, now could be written down in a formula pretty much similar with the ones that we have over here. What's the difference? The only difference is that instead of having an integral to build up your Fredholm determinant, you have really a series, a single series, and it's not an arbitrary series, but this series is precisely the discretization of this contour. Okay, ugly formulas, I agree, especially if you're not familiar with Fredholm determinants, but perhaps you're familiar with Fourier series and Fourier transform. And this is the precise analog. So sort of you have a certain Fourier transform here with a cubic term, and we just managed to get a Fourier series now. So sort of we have a discrete, so the periodic Tay-Sap is a discretization of the classical Tay-Sap, or the limiting fluctuations of the periodic Tay-Sap become just a discretization of the classical Tay-Sap. The discretization here is not any discretization. The contour is specific and encodes also the periodicity. Because this gamma, everything that we have should be periodic in gamma, because we're talking about periodic Tay-Sap, right? Anyway, let's not stick to the details, but this analogy. So to a certain extent, we are explaining why, how to go from classical to periodic, just discretized to some extent. Okay, and the second result I want to tell you, and this is, okay, so you have like 10 minutes. Okay, so the second result I want to tell you is somehow a formulation which doesn't rely on Fredholm determinants, but instead on an equation, on a differential equation. Let me just remind you that for the classical Tay-Sap, the limiting distribution was just determined by a second order nonlinear ODE, the Spanavec equation. You still needed to solve the equation, certain boundary condition, take some integrals, exponentiate, and then you will recover the distribution. Anyway, and our result is somehow analog. So, okay, you start with this limiting distribution, there's still a superposition, but then you take the core part, non-explicit part, which is the Fredholm determinant. And we prove that the second log derivative splits into a product of two functions. Right, so sort of similar to what we have over here. Right? But instead of one single function, the u, now is this u is being replaced by p times q. But what are those two functions? Those two functions, there are two ways to see them. They either, you can see them as either solving like what we call a couple MKDV system or a couple couple system of heat equations. Okay, there what they are, right? Some partial differential equations. Later, I'm going to say why we care. Well, okay, they are what they are. Okay, but then you're going to see that some of them, so depend on two variables. One of them is time and height. The other one is space and height. But actually, they have multiple solutions, P and Q. And when you combine them, you get some compatibility. And actually, what we get is that if you look now at the product, U here is really the product P and Q. It solves like a next order equation, which is this KP equation. It's a model for short nonlinear waves in two dimensions. Anyway, at this stage, let's just take it. Okay, it is what it is. What's the output here? Well, if you're doing it the classical Tay-Sap, to get this limiting universal distribution, you simply needed to solve a nonlinear second order ODE. Now in the periodic Tay-Sap, you depend on trivially on three parameters. Life is not so easy. And at the end of the day, what you really need to do is that you need to solve, to describe the limiting distribution, you need to solve a fourth order PDE in three variables, two spatial, one temporal variable, and this PDE appears also in the context of nonlinear 2+1 dimension waves. Okay, it is what it is, but we found it nice. Sort of an equation, universal equation in nonlinear waves now appeared here. Okay, more about that in a moment. Okay, I want to just give, I don't plan to tell, of course, the details of the proof. The formulas are not necessarily simple, but the methodology is sort of instructive as well. And that's essentially where integral systems comes into play, and that sort of explains why we care about those interpretations, right? But I just want to make an analogy on how things appear the way they appear. For that, let me just remind you that how do you solve, let's say, linear PDEs? Do like a first order PDE class. Well, you have a linear PDE here. Well, you have, so you can see that as an evolution. You start with a certain profile you evolve with time according to your PD, and you get a final profile at a later time. Well, this one perhaps you can solve directly, or you can just do Fourier transform. And when you do Fourier transform now, you have an initial profile in a new variable. What's the advantage? The advantage is that the new profile, the evolution here, doesn't take place in two variables, but only in one variable. And moreover, it's like a first order ODE now. And you can evolve it easily. You solve it explicitly in this case. And then what you do, you just reverse Fourier, and then you get your final solution, right? But this is for linear equations. For nonlinear equations, life is not so simple. Imagine that you have a nonlinear evolution. Bear in mind this KP equation, 2 plus 1 dimensional equation, nonlinear, that describes waves, evolution of waves. Set a very nonlinear evolution. Okay, you cannot rely on just solving it exactly. There's one thing that we call a scattering transform, which plays the role of Fourier transform. You associate with the spectral problem, you find eigenvalues, eigenvectors, you find evolution of this spectral data. Anyway, and the point is that if you do that properly, the scattering transform, which plays the role of the Fourier transform, is not linear, it's nonlinear. It's a spectral problem. But if you succeed, you get a linear evolution in this new space, in the spectral variables. Oh, nice. So now I can solve in the spectral variables, but they have to move back. And then it comes another transform, which is the inverse scattering transform. Not so easy as Fourier and inverse Fourier. But they're there. What does this have to do with what we do? Okay, first off, for going there, the point is that unlike Fourier transform, it's sort of canonical for any linear equation, inverse Fourier transform, inverse scattering, they are equation dependent. If you change your nonlinear evolution, you're going to have to adapt your scattering, inverse scattering transforms. And they are highly nonlinear, but if you're lucky enough, the equation that you get actually admits a scattering, inverse scattering transform, and that's what we call integral equations. Here, the name integral system. Although the equation is complicated, it's nonlinear, can imagine it's an infinitely dimensional dynamical system, you can still solve it doing transformations. Right? Here, as I say, the scattering transform comes from spectral theory, like pairs, and the inverse scattering transform is what we call a Riemann-Hilbert problem, typically. Anyway, but it's still equation dependent. Finally, what does it have to do with all that? Remember, what we do is that we start with our Fredholm determinant. We do lots of mumbo jumbo. We transform our determinants and whatnot, and then we realize that somehow we reduce it to still a Fredholm determinant, but the operator that we get is a projection operator. And the point is that associated with this projection operator, you have a boundary value problem in one variable, so a complex, better to say, complex function problem, which essentially says, if you know a matrix value function at infinity, can you recover this matrix value function, the whole complex plane? Okay, that's coming from this Fredholm determinant, this projection operator approach. But now, okay, we get this problem, and we recognize that this problem is precisely the inverse scattering problem for the, let's say, KP equation, for all the system that we have. Hey, look at that. We start with something that gets to a certain complex value problem. And on the other hand, this complex value problem is precisely the one that arises in the KP equation. So we just match them, match parameters, match everything, and then suddenly, okay, so we see that the Fredholm determinant and whatnot is just like a solution to the KP equation, right? Or the other systems as well, right? Okay, just to get an idea. So basically what we do is nonlinear inverse transform. We are lucky to do, so coming from the side of Fredholm determinants, we are lucky to arrive at a certain expression which can be recognized as the inverse Fourier, nonlinear inverse Fourier transform of a nonlinear wave equation. Okay, and then the connection is done, right? One can do the same for actually the classical Tay-Sap. We did for the periodic, but for the classical Tay-Sap, one can do the same and then recognize the Panevet-2 equation, the classical result of Peter Forster and Tracy Whedon, although they didn't do that way, but one can do the same. Those techniques, they have been around for more or less like 10 years perhaps, but they are model dependent. It's quite some work for one specific, let's say, periodic, in this case, periodic Tay-Sap to carry out all this program. Okay. And there's no, I mean, before you do and you get there, you can never guess what equation you're going to arrive at the end, right? Well, we arrive at this KP equation, right? Okay, moving towards the end. Why we care about that? The point is that once we make this connection, we can use tools from integral systems to make to answer questions on probability, right? Okay, first off, long time asymptotics. We have this oh, this shouldn't be FKPZ. This should be just the F for the periodic Tay-Sap. Sorry for that. So the first question is, okay, what happens with this distribution of the periodic Tay-Sap when time goes to infinity? Well, we find that the distribution of periodic Tay-Sap just converges to a Gaussian when time goes to infinity. Well, it is to be expected. Remember, at the very beginning, periodic Tay-Sap, time runs for a very long time, much faster than the period. All the particles move together, so you're a single block. So really, in one end, this new distribution F really becomes fluctuations of Van der Waals. What about the other end? Well, if your period scales much faster, it means that you should be recovering the classical Tay-Sap. Well, we are able to do that. Still for gamma equals 0, it's the position. Well, things get technically very complicated if we don't do position 0, but okay, for another story. And again, this should be F, not FKPZ. Sorry for that. And particularly interesting for perhaps reliability. Okay, so those first two questions basically say, well, this new distribution really interpolates between Tracy-Weedon and Gaussian. In other words, interpolates between the classical Tay-Sap and Van der Waals, single Van der Waals fluctuations. Another one, upper tail. We can access upper tail. So if you look at this distribution, when X goes to infinity, what we get is that for almost every position, it's basically the same tail as the standard classical Tay-Sap. There's one sudden case, which is this when gamma is exactly a half. What does that mean? Remember that we have periodicity, and we have this position where the first particle of a group hits the last particle of the other group. And this creates a certain shock, and that's why you have a square here. So sort of you get this Tracy-Weedon distribution squared for the tail of this new distribution when you are exactly following the shock of particles of different groups. Anyway, some of the techniques here, some of those proofs, they really came like nicely once we realized that we have connections with integrable systems. Right? Okay, but actually, okay, so time to wrap up. Okay, we walked through several things, but if you didn't get much, just get this. What we did is, okay, we have a limiting one-point distribution of periodic Tay-Sap, ugly formula. What do you do with that? We managed to connect with certain equations that appear in nonlinear wave theory. There's actually, we're working on generalization. You could look, in this case, we look at for one-point distributions of the height function, but you could look at multi-point distributions, start looking at correlations between different points, different times, different heights of your evolving random surface, random graph. And there are analogs. We're working on the analogs for those limiting distributions. Yeah, for instance, there now those wave equations take now a matrix form, and that's particularly interesting because in the context of KPZ fixed point, Kostel and Remenick found recently also some connections with different wave equations, and we're sort of generalizing their results. Anyway, for another day. And of course, I talked about large tail, so upper tail of this new family of distributions in the periodic Tay-Sap, and now we're working also in the lower tail, which usually is much harder. And here, there's no way. We have to rely on integrable systems, and that's work in progress. We still don't have results. We hope to have perhaps in a year, but then we really need to use integrable systems techniques to handle the lower tail here. Okay, talk too much. Thanks a lot.
Thank you, Guilherme. It was dense. That was really nice. You're very good in explaining stuff which really are very difficult.
Well, thank you. Thank you. I hope you at least got some idea. Of course, formulas, but at least some ideas of what kind of connections appear.
It was really good. Thank you. Anyone has any question or comment? Vladimir, with your microphone open, I'm not sure if you want to make a question or is it just... No? Okay. I have a question just to be sure, because you said in the beginning that actually now what you have is some theorems which are very model relying, right?
Yes.
So this is because your way of solving this inverse scattering transform or not? Why is so model relying? This is my
Okay, so to some extent you're right. To some extent you're right, but perhaps because the point is that they're like sort of bigger bags, so to say. So you have this very big bag, which are the models that you expect to be in the KPZ universality class. So that fluctuation should be universal and described by whatever quantities we have available. Right? It's universal quantities like the Tracy-Wheaton or variance. You have a smaller bag, which is the one where you have explicit formulas. This comes into the framework of what people call nowadays integrable probability. You have techniques in representation theory that allow you to solve exactly basically Kolmogorov equations. You solve exactly, although ugly. So the smaller bag. In this smaller bag, you can compute some statistics, and you can verify through those explicit formulas that you have this limiting object. And you have an even smaller bag, which is the ones for which the formulas are not just ugly, but they have their inner beauty. And in their inner beauty, you realize that there is some connection with integral systems. We thought that that was very specific, but, and that's also work in progress with Bacon and Prokhorov, we actually finding sort of expanding this little bag that connects to integrable systems. Right? So sort of those three layers. Okay. Models, more or less explicit formulas for the models, and connection to integrable systems, which are sort of the smaller one. But I guess the point is really that and once you have the connection with integrable systems, you get more techniques. And in that sense, you have more power to prove results and to analyze things like concretely. But the fact that you don't have really, you cannot do much in generality just for specific models, it's still because, I mean, all the techniques we have available still rely somehow on explicit formulas. Well, for several reasons. First, because, well, that's what people could cook up so far. It is what it is. Perhaps there's like people will just invent something new. Secondly, also because even the limiting object, this limiting two-dimensional fluctuation field, this KPZ fixed point, whatever it is, it was just described 3 years ago, 4 years ago. Okay. So we didn't even know how to access how to describe the limiting object itself. We could only compute its statistics, but without describing the object that actually has those statistics, right? So at that point, we were really computing everything, just doing particular statistics, not really describing the whole dynamics. Right?
So once you have these particular models, is there any example of this in the beginning where you can actually solve your PDEs and have a explicit form for your density?
No.
I mean, no.
No.
This is nice because usually when you are able to do this explicitly, like solve the equations and have a density, you have a very nice interpretation on the physics, right? This is why it's nice having equations in the end of the day. Like,
yeah. Well, no, there's no neither. No, there's no hope. Well, there's no hope. But again, that's the point. Also, but the point is that once you have connections with integrable systems, you don't need to be so explicit. You can still analyze quantities like tails and whatnot.
I do agree that you don't need it, but it's nice to have some of them in hand and see in physics. This is right.
No, I get no. Then it's really hopeless. Okay. It's highly nonlinear models, so in that sense, it's really Gaussian. If you're dealing with Gaussian universality, okay, good, cool. If you, in that case, in those particular statistics that we're talking about, no. Even those equations do have some very particular explicit solutions, but those very particular explicit solutions are not the ones that arise in probabilistic models.
Okay.
So,
it's a pity.
Yeah.
So, if anyone, if no one...
Yes, I have a question.
Okay.
Yes, please.
I understood that you're either already proved or in the process of proving what I'm going to call finite dimensional convergence. I'm not sure if that's the appropriate.
I guess you're talking about this one.
Yeah.
Yep. Mm-hmm.
So do you expect to get, or is it known that we have tightness in any decent space for this process?
Good question. Okay, so in the context of ASAP, so when we talk about those multi-point distributions, so those marginals, so multi-point marginals, so you have like this limiting object to dimensional fluctuation field, and then we're looking at multi-point marginals of this field. The fact that the ASAP converges to some limiting marginals, this is done like last year by Baek as well and Jipeng Liu. The formulas are not explicit. And then we're starting from that and trying to see what we can get in terms of, for instance, differential integral systems and whatnot. But now that's very in terms of really like the TASAP, so very concrete, and those convergences are really in distribution, right? I'm not so. If I understand correctly, I guess you're talking about what type of convergence you can get in terms of the processes themselves, right? Not only convergence in distribution. Did I understand correctly?
Well, it's the convergence of the distribution of the full. It's like when you prove convergence of random walks to Brownian motion. So you can get some finite dimensional convergences, and then you can
no, at this stage I won't say no. So at this stage what we know is proven in the literature is really the finite dimensional ones, as I said, as you have for instance like the easier one for random walk to Brownian motion, right? But if you really want to prove convergence of the whole process, I guess so this is done for one model, if I remember correctly, by the same, I guess this is done by Duncan Del Vergne and Balin Virag in the context of last passage percolation. So it's another model, you can relate it to the TASAP, and for that specific model, they do have convergence of really the 2-point field to this two-point field of the KPZ universality. I don't know how they do that. If they really go to multi-point, let's say to those to those finite dimensional marginals, and then prove some tightness, or if they just do direct with other techniques. This I don't know. But in the context of KPZ universality class or KPZ fixed point, I'm only aware of this convergence for last passage percolation. It's sort of related here, but not for the TASAP as far as I can tell. And this is done, it's on the archive, perhaps was done like later last year. So, or early this year. It's very, very, very recent. Yeah.
Okay, thank you. Thank you for an excellent talk.
Yeah, thank you.
If no one has any other question or comment, let's thank Guilherme for the talk. Thank you, Guilherme.
Thank you, Lynn. Thank you all.